And here we are again. We are at, thanks for being here today. We're here at section 9.2, estimating a population mean. Previous section was a population proportion. Now we have a population mean. The first thing we want to do is obtain a point estimate. Point estimates are just take a sample and estimate what the population is with that sample. And the mean is going to be well, kind of the average weight of a penny, right? We already did the fraction of people that believe a certain way. Now we're into maybe back to that average weight of a penny. We're looking for the population, but not measuring every penny that's out there because that would be impossible to do. I don't think I need to talk much about this slide. Moving on right to our example. Let's say this list of 17 randomly selected pennies has weights given. Let's treat this as a simple random sample of pennies and estimate what the population is. Now the US Mint, of course, is probably going to say, well, you don't need to estimate, we'll tell you what the penny's weight should be, but maybe we don't trust them or we don't know what it is. We can use this to estimate what it is. And the way we would do this is simply, add these all up and divide by 17. Naturally, where is the stat print screen? I found it. I think it's right there. So I have the 17 pennies put in there. I've even named the column heading as penny weights. And I could go to statistics, some summary stats of this column. This is the column. I scroll down, hit compute, and it tells me, I don't know if you can read it very well, but along with all the other stuff, it tells us that the mean is 2.464. And that's the point estimate. I've probably got a few more things to do with this data here, but that is what we have. Let me go back to our PowerPoint. And now we move into something a little more bizarre, a little comical at times, and what we call students' T distribution. Sample portions were easier to do, and it's mostly because we're not going to sample 4 people or 17 people. Even in our quantitative analysis, we said let's sample 30 or more. Right? We can do large numbers of samples, but occasionally when we're working with sample means, or even with proportions, I suppose, but working with sample means, the sample sizes can get pretty small. And that leads to some consequences that we'll discover right here. But sample proportions, it was pretty easy to do using z-scores. Sample means are going to be a little bit more difficult. You know what normal curves are? They're normal. It's what we see in the normal world. But we're going to move away from normal curves for a little bit and realizing that these specifically were z-scores using a population standard deviation. When we're working with samples, we don't know the population standard deviation, so we cannot use z-scores or the normal curve. So everything that we've been talking about, the normal curve and z-scores, recognize that's just one portion of statistics. There are other distributions out there, z-scores and normal. Now we have t-scores and what should be called the Gossett Curve. I think I spelled that wrong. Sorry, I should have 2 T's. My bad. And what should be called the Gossett Curve, but is not called the Gossett Curve. William Gossett worked for Guinness Brewery. He was working on the best mixture of grains, but he had to use very small sample sizes. And when he applied a normal analysis, things just didn't work out quite right. So he developed a new technique, and instead of using the letter Z, he used the letter T, maybe because that's the missing T in his name. I really need to go fix that. I'll fix it so when you're looking through the PowerPoint with me, you'll see the typo fixed. So now we have z-scores and t-scores to work with. And the question comes, and I fixed it here, the question becomes, why isn't it named the Gossett Curve? And well, he really wanted to publish his results. He really did, not just because he wanted recognition for himself, that's obvious, but he wanted it to be analyzed and vetted by other statisticians of the day. He had this idea and he wanted to put it in the journals of the day so other people could look in and say, hey, what do you think of this? Is it this? Is it this? Did I do this right? But Guinness, his employer, wouldn't let him do that. Apparently, Guinness had been burned by other employees that were selling trade secrets to other competitors. So he would not let them publish anything under their name because it could be potentially tracked back to the Guinness brewery. So none of his employees could use a real name. So Gossett is going to use a pseudonym, a fake name. And he could use any name he wanted, right? He could pick any name. So what name did he pick? He picked the name Student. Student. So this is called Student's T distribution, not Gossett's T distribution, but Student's T. I guess he was just a student of statistics, and that's what he wanted to do. So anyway. So this is what Gossett's technique did. It used the sample standard deviation instead of the population standard deviation, along with some other modifications. And this is the biggest thing that he noticed. Depending on the sample size, the shape of the curve is different. So we have a normal curve. A normal curve is always the same shape. Remember how we normalized data to compare my height to my wife's to the two basketball players, or to compare the size of a grape to a watermelon. The size is always the same. However, the t distribution, not only is the t distribution a different shape than the normal distribution, the t distribution is different within itself depending on the sample size. A sample size of 5 is going to have a different t distribution shape than a sample size of 10, a different one than a size sample of 50. So the t distribution shape changes continually. Now, one thing that is true, which is why we can use the normal distribution to predict things with proportions, one thing you notice is that as the sample size becomes larger, the shape of the the shape of the t becomes the same as z. The shape of the student's distribution becomes the same as the normal distribution for sizes, sample sizes that are fairly large. So this is going to be an analysis that is used for small sample sizes. And let me scoot forward to show you the z-score is computed, the t-score is computed. They're both the same here, but instead of dividing by the reduced population standard deviation, we're dividing by the reduced sample standard deviation. That is really the only difference for this. I'm going to let you pause the video and read through that. Oh, wait, don't pause yet. N-1 degrees of freedom. What in the world is that about? I'll get to that in a minute, but let me say right now that if every one of these student distribution shapes is different, we have to have a way of naming them. That's a very, very loose way of describing degrees of freedom. But depending on what the sample size is, subtract 1, that tells you your degrees of freedom, and that is what tells what the shape actually looks like. So the sample size is exceedingly important here. So scooting forward, note the differences between them. I already did. One uses the population, the other uses the sample. Z-score is used for smaller sample size. They can both be used to model. So here's the picture. The blue on the outside is your normal curve. And what you notice is if you have a T students distribution with a small sample size, there's a lot more variability. The tails are going to be a lot larger. There just hasn't been enough data to really narrow some detail down, I guess. In any case, the larger the sample sizes get, the taller the peak gets, the smaller the tails get, and we end up with a normal sized curve. So some observations here. Z is symmetric, so is T. It's bell-shaped, it's pretty much bell-shaped. Centered at 0, yep, so is T. Rectangles between -3 and 3. I don't remember what I meant with rectangles. I think that means that pretty much all of your data is going to be within 3 and -3. But here you've got much longer tails and it's much more dispersed. It is unlikely that it is normal. And this additional spread is because we use S, the sample standard deviation, to find T instead of the population. Okay. Oh, that's right. The sample standard deviation is itself a random variable, so it's going to be all over the place instead of a nice fixed population standard deviation, which is much more rigid. If you take a sample, it's going to have a different standard deviation, which affects the shape of the curve. Continued. Yep, degrees of freedom I already talked about. It is different for different sample sizes. That's the shape. Centered, symmetric. The area under the curve is 1. The area to the right is a half, and to the left is half, just like before. And it gets closer and closer to 0 as we go. I'm repeating a whole lot of things here. Sorry about that. Let's just determine some T values. Okay, I'm going to introduce a new vocab for you, which is called critical values. And the critical values are an important concept because those refer to the fences, the boundaries that we have between what is normal and what is abnormal. In some way, we've already talked about critical values a lot, but we're gonna more precisely talk about them now. Critical values are values on any distribution, a normal, which is Z, a T, here's a chi-square. That's a little hint to what's coming up next. There's actually 3 distributions that we talk about in this class. Normal, we've spent a lot of time on, T that we're spending some time with now, and the chi-square that we'll spend a brief bit of time towards the latter parts of the class. And the critical values then are the boundary between what is usual and expected and what's going to be in the tails or as unusual. And we could have boundaries that give us the 68% of data for a normal, that's plus or minus 1 standard deviation, or a critical value of plus or minus 2 would be a value on the graph that separates out the 95 and the 5%, 2.5 in each tail, and so forth. They are often figured out using classical computational. We're gonna, a lot of times actually with technology, we kind of skip over it and let the technology determine if it's usual or unusual. But they're important to know. And when we get to this stage in the class, we then have 2 numbers to compute. The boundary, and we also have the test statistic. So if you think about it this way, you're going to establish where your fence is. And then you're going to let the data speak for itself, and the data will be somewhere on this continuum of the normal curve. And if the test statistic is inside the fence, then it's fine, it's normal, it's usual. But if the test statistic is outside the fence, then it's going to be considered something unusual. So we're comparing the 2 values. We're comparing we're finding two values. We're finding where the critical value is, and then is the test statistic inside the fence or outside the fence? And that is what we're going to work with. So here's the shape of our T-curve with a particular degree of freedom that is unknown. This right here could be a critical value based on an alpha. Let's say the alpha is 0.2, which means here is an area of 20% or 0.2. This would be an area of 0.8. And I want to know where this boundary is. In other words, how many T values, not Z values, but how many T values do I have to go up before I reach before I cut off an area of 20%. So let's do this example. Find the T value, the critical value, or the boundary, such that the area under the T distribution to the right of that T value is 20%, 0.2, assuming 10 degrees of freedom. That is, find the T sub 0.2 with 10 degrees of freedom. What does the 10 degrees of freedom mean? Well, maybe there was a sample size of 11. Right? Maybe I collected 11 pennies instead of 17. If I collected 11 pennies, then I'm going to have the shape of a degree of freedom 10. And that degree of freedom 10 shape is going to have a boundary in a slightly different place than any other degree of freedom. So what does this? What might this look like? Well, we've got this right here, 0.20. The area is 0.20. So how do we find this area? Well, there's a chart that is in the back of the book, right? Well, I found out that I have a PDF copy of that chart, so it has been loaded into Canvas, so you have that. And if we go to that chart, I think it's on the last page. Oh, there it is, right here. So if we go to this chart, you'll find this, I think it's table 6, and it should look something like this. You can see it's a T distribution. And if you go down, I think I can make this a little bit larger. If you go over to a degree of freedom of 10 with an area of 0.20, those things match at 0.879. So 0.879 is our boundary. That's our critical value, which means, going back to here, 0.879, that is, you need to move over 0.879 standard deviations from the middle to find where that boundary is. That boundary separates the top 20% from the bottom 80%. And if we wanted to have a smaller, maybe not 20%, but maybe 5%, now we can separate what is usual from what is unusual. Okay, so now, whoops, not what I wanted. I pushed the wrong button. Okay, so now let's construct and interpret a confidence interval. This becomes very similar to what we did in section 9.1. It's just using a different section of our StatCrunch. Very little time in the classical methods and much in favor of the technological. The problems that you'll have in the homework are either going to give you data, like I gave you the weights of the 17 pennies, or summary statistics, like we had with the 1123 over 1783 proportion. That was summary statistics. Maybe there'll be a situation where they say 17 pennies were collected and the mean of those pennies was this. That's summary statistics. Sometimes they might say, here are the weights of 17 pennies. That's the data, right? In any case, you have the ability to use StatCrunch for that. So let's construct let's construct 99%, 95%, and 90% confidence intervals about the population mean weight of these pennies. So how do I go about doing that? Well, if you recall, I still have the penny weight in here. I'm going to get rid of this calculator here, and what I'm going to do is I'm going to do now not proportion stats, but T stats. And I have one sample using data, not the summary, but the data. So the data is going to be the penny weights. I do not want hypothesis test, I want confidence intervals, and I'm only going to do one of these, just the 0.9. And I can click compute, and it looks like I've got, and just a couple of things to notice. First of all, the mean is the same, the 2.464 is the same mean. Here's the standard error, which probably goes back to that standard deviation idea. Degrees of freedom of 16. Why 16? 17 pennies. 17 pennies were collected. 17 minus 1 is 16 degrees of freedom. And then I can compute then the lower and upper limits from there. So if the mean is 2.464, 2.457, 2.472 become my lower and upper limits, and from that I can find my margin of error and different things. That is all there is at this point about Chapter 9. I think there are 3 sections that you're doing in Chapter 9, I think, but there's only 2 lecture sections. I don't think there's anything for Section 3. If I determine that there actually is, then I'll throw another video up about things. You've been great about asking questions. Actually, not many of you do. So if you have questions, please feel free to, as you move back into the, I guess this will be almost the first homework section that you haven't had a whole lot of interaction with me in person. So please put me to work and let me know how I can help you. See ya.